Good day, ma'am. My name is Joseph D. Machado Jr. from BC1B. That's from the topic Lecture for Series and Parallel Circuits. Example 10.2 Equivalent resistance, current, and power in series circuit. A battery with a thermal voltage of 9 volt is connected to a circuit consisting of 420 resistor and 110 resistors, all in series, figure 10.13. Assume the battery has negligible internal resistance. A. Calculate the equivalent resistance of the circuit. B. Calculate the current through each resistor. C. Calculate the potential drop across each resistor. And lastly, determine the total power dissipated by the resistors and the power supplied by the battery. So this is parts of resistor. Resistor 1 is equals to 20 resistor, and so on and so forth. So negative and positive voltage is equals 9 volt. Figure 10.13, a simple series circuit with 5 resistors. Strategy: in a series circuit, the equivalent resistance is the algebraic sum of the resistances. The current through the circuit can be found from Ohm's law is equal to the voltage divided by the equivalent resistance. The potential drop across each can be found using Ohm's law. The power dissipated by each resistor can be found using potential is equals to I, or initial, square resistor, and the total power dissipated by the resistor is equals to the sum of the power dissipated by each resistor. The power supplied by the battery can be found using potential is equals to initial, E node. Solution: A. The equivalent resistance algebraic sum of the resistances resistor sub S is equals to R sub 1 plus R sub 2 plus R sub 3 plus R sub 4 plus R sub 5 is equals to 20 resistor plus 20 resistor plus 20 resistor plus 20 resistor plus 10 resistor is equivalent to 90 resistor. B. The current through the circuit is the same for each resistor in a series circuit and is equal to the applied voltage divided by the equivalent resistance. So this is the formula. Initially is equals to volt over R sub S is equals to 9 volt over 90 resistor is equals to 0.1 amperes. Then C, the potential drop across each resistor can be found using Ohm's law. V sub 1 is equals to V sub 2 is equals to V sub 3 is equals to V sub 4 is equals to 0.1 ampere multiplied by 20 resistors is equivalent to 2 voltage, and V sub 5 is equals to 0.1 ampere is equals times 10 resistor is equals to 1 volt, and V sub 1 plus V sub 2 plus V sub 3 plus V sub 4 plus V sub 5 is equals to 9 volt. Note that the sum of the potential drops across each resistor is equals to the voltage supplied by the battery. D. The power dissipated by a resistor is equals to potential is equals to initial square resistor, and the power supplied by the battery is equals to potential is equals to initial, P sub 1 is equals to P sub 2 is equals to P sub 3 is equals to P sub 4 is equals to the quantity 0.1 ampere square multiplied by 20 resistor. So the total is 0.2 watts, and P sub 5 is equals to 0.1 ampere square times 10 resistor is equals to 0.1 watts. P dissipated is equals to 0.2 watts plus 0.2 watts plus 0.2 watts plus 0.2 plus 0.1 watts is equals to 0.9 watts. P source initial is equals to anode is equals to 0.1 ampere times 9V. The total is 0.9 watts. We could use multiple resistors instead of just one resistors with a resistance equal to the equivalent resistance of the circuit. Perhaps a resistor of the required size is not available, or we need to dissipate the heat generated, or we want to minimize the cost of resistors. Each resistor may cost of a few cents to a few dollars, but when multiplied by thousands of units, the cost saving may be appreciable. Continued in Lecture 4 Series and Parallel Circuits, Example 10.3, Analysis of a Parallel Circuit. 3 resistors, resistor sub 1 is equals to 1.00 resistor, R sub 2 is equals to 2 resistor, and R sub 3 is equals to 3 are connected in parallel. The parallel connection is attached to volt is equals to 3 voltage source. A. What is the equivalent resistance? B. Find the current supplied by the source to the parallel circuit. C. Calculate the currents in each resistor and show that these add together to equal the current output of the source. D. Calculate the power dissipated by each resistor. And lastly, find the power output of the source and show that it equals the total power dissipated by the resistors. Strategy. A. The total resistance for parallel combination of resistor is found using this formula. R sub P is equals to submission and 1 over R sub 1 negative 1. Then B, the current supplied by the source can be found from Ohm's law. Substituting R sub P for the total resistance initially is equals to V over R sub P. Then C, the individual currents and are easily calculated from Ohm's law. Then initial sub 1 is equals to V sub 1 over R sub 1. Since each resistor gets the full voltage, the total current is the sum of the individual currents. I is equals to submission. So this is the formula. Then the power dissipated by each resistor can be found using any of the equations relating power to current, voltage, and resistance. Since all three are known, let us use P sub 1 is equals to V square IR. Since each resistor get full voltage, E, the total power can also be calculated in several ways. Use potential is equals to IV. Solution. A. The total resistance for a parallel combination of resistors is found using equation 10.3. Entering known values gives Rp is equals to quantity 1 over R sub 1 plus 1 over R sub 2 plus 1 over R sub 3 negative 1 is equals to the quantity 1 over 1 resistor. So, mo na siya atong R sub 1. Then, plus 1 over 2 resistor is our R sub 2. Then, plus 1 over 2 resistor is our R sub 3. We are going to substitute. So, the total is 0.50 resistors. The total resistance with the correct number of significant digits is Rp is equals to 0.50 resistor. As predicted, Rp is less than the smallest individual resistance. B. the total current can be found from Ohm's law since each resistor gets the full voltage. Thus, initial is equals to V over R sub P is equals to 3 volt over 0.50 resistor. So we're going to substitute, then the answer is 6 amperes. Current 5. Each device is much larger than for the same devices connected in series. See the previous example. A circuit with parallel connections, a smaller total resistance than the resistors connected in series. C. The individual currents are easily calculated from Ohm's law since each resistor gets the full voltage. Thus, I sub 1 is equals to V over R sub 1 is equals to 3 volt square over 1 resistor. So we're going to substitute, then this is the answer, 9 watts. Similarly, I sub 2 is equals to V over R sub 2 is equals to 3 volt square over 2 resistor. Then the answer is 1.50 amperes. And I sub 3 is equals to V square over R sub 3 is equals to 3 square over 2 resistor. So the total is 4.50 watts. And E, the total power can be also calculated in several ways. Choosing P is equals to IV, so this is the formula, and answering the total amount yields P is equals to IV is equals to 6 amperes, then multiplied by 3 volts, so the total is 18 watts. Significance: total power dissipated by the resistors is also 18 watts. P sub out is equals to I square sub 1 R sub 1 plus I sub square sub 3 R sub 2 plus I square sub 3 R sub 3 plus I sub square sub 3 R sub 4 is equals, the total is 130 watts. Note that the solution for the current I sub 3 is a negative. This is the correct answer, but suggests that the arrow originally drawn in the junction analysis is the direction opposite of conventional current flow. The power supply with the second voltage source is 58 watts and not negative 58 watts. So let's going to proceed. Example 10.6, calculating current by using Kirchhoff rules. Find the currents flowing in the circuit in figure 10.29. So figure 10.29, this is the circuit. Then it's combination of series parallel configurations of resistors, voltage sources. This circuit can be analyzed using the techniques discussed in electromotive force, but can be analyzed using Kirchhoff rules. Strategy: this is circuit sufficiently complex that currents cannot be found using Ohm's law and the series parallel techniques. It is necessary to use Kirchhoff rules. Currents have been labeled initial sub 1, initial sub 2, and initial sub 3 in the figure, and the assumptions have been made about their directions, locations on the diagram. Been labeled letters are true. In a solution, we apply the sanctions and loop rules, seeking the independent equations, and follow us to solve for the 3 unknown currents. Solution: applying the junction and loops rules yields the following 3 equations. We have 3 unknowns, so 3 equations are required. Junction C, initial sub 1 plus initial sub 2 is equals to initial sub 3. Loop ABCDE FA, initial sub 1 multiplied by R sub 1 plus R sub 4, negative initial sub 2 multiply R sub 2 plus R sub 5 plus R sub 6. The total is V sub 1 negative minus V sub 3. Simplify the equations by placing the unknowns on one side of the equations. Junction C, initial sub 1 plus initial sub 2 minus initial sub 3. The total is 0. Loop A, B, C, D, E, F, A. Initial sub 1 multiplied 3 resistor minus initial sub 2 times 8 resistor. The total is 0.5 volt minus 2.30 volt. Loop C, D, E, F, C. Initial sub 2 times 8 resistor plus initial sub 3 multiplied 1 resistor is equals to 0.6 plus 2.30 volt. Simplify the equations. The first loop equation can be simplified by dividing both sides by 3. The second loop equation can be simplified by dividing both sides by 6. Junction C, initial sub 1 plus initial sub 2 minus in sub 3 is equal to 0. Loop A, B, C, D, F, A. Initial sub 2 multiplied by initial 8 resistor minus initial sub 2 times 8 resistor. The total is negative 1.8 volt. Loop C, D, E, F, C. Initial sub 2 multiply 8 resistor plus initial sub 3 multiply 1 resistor. The total is 2.9 volt. Significance: a method to check calculation is to compute the power dissipated by the resistors and the power supplied by the voltage sources. Calculating the current by using Kirchhoff rules. Against, find the current flowing in the circuit, figure 10.30. The circuit consists of 3 resistors and 2 batteries connected in series. Note that the batteries are connected with opposite polarities. So this is 3 resistors and the battery. Strategy: this circuit can be analyzed using Kirchhoff rules. There is only one loop and no nodes. Choose the direction of current flow. For this example, we will use the clockwise direction from point A to point B. Point A, point B. Consider loop A, B, C, D, A and use figure 10.23 to write the loop equation. Note that according to figure 10.23, battery K sub 1 will be added, a battery V sub 2 will be subtracted. Solution: applying the junction rule yields the following 3 equations. We have one unknown, so one equation is required. Loop A, B, C, D, A, negative 1 sub 1 minus V sub 1 minus 1 R sub 2 plus V sub 2 minus I R sub 3 is equals to 0. Simplify the equation by placing the unknowns on one side of the equations. Use the values given in the figure. I initial multiplied by R sub 1 plus R sub 2 plus R sub 3. The total is V sub 2 minus V sub 1. So, this is the formula: V sub 2 minus V sub 1 over R sub 1 plus R sub 2 plus R sub 3 is equals to 24 volt minus 12 volt over 10.0 resistors plus 30 resistor plus 10 resistor. So, we're going to substitute. So, the total is 0.20 amperes. Significance: the power dissipated or consumed by the circuit equals the power supplied to the circuit, but notice that the current in the battery V sub 1 is flowing through the battery from positive terminal to the negative terminal and consumes power. P potential R sub 1 is equals to initial square R sub 1 is equals to 0.40 watts. P potential R sub 2 is equals to initial square R sub 2 is equals to 1.20 watts. Potential R sub 3 is equals to initial square R sub 3 is equals to 0.80 watts. Potential V velocity sub 1 is equals to initial V sub 1 is equals to 2.40 watts. P dissipated is equals to 4.80 watts. P potential sub source is equals to initial velocity sub 2 is equals to 4.80 watts. The power supplied equals to the power dissipated by the resistors and consumed by the battery V sub 1.